first, let's talk a little bit. Today is Wednesday. Tomorrow is your last guided lecture of week 2, or essentially sprint 2. Tomorrow's an exciting lesson because we finally actually get to turn things around and start predicting stuff. But before we get there, we've got one more lesson to cover and to kind of make sure we've rounded out the world of inferential and the philosophy of statistics that you can expect to see on a lot of different levels. So today we'll be diving into Bayes' theorem. This is a very introductory lesson on Bayes' theorem, just like kind of the field of statistics is huge. The field of Bayesian statistics is just as expansive, and the way the two fields kind of intersect and contradict and argue with each other is really fascinating to watch if you're just coming into statistics at a different stage in your life. I think a lot of folks who are doing career transition or who are beginning introduction to statistics in an academic setting get to kind of hear a lot of the academic disagreements between these two different fields of statistics. But then what I like about the component of studying this from a kind of career transition is that both of these fields are very much philosophically interesting to convert from a real world business application, because it seems fairly obvious when you kind of look at the philosophy of one component versus the other. And yet there's so much controversy as to how you can mathematically assign certain probabilities or certain components of the topic we're going to be talking about today. But before we get into that, I just want to make sure that we are aware that tomorrow you have your second sprint project due. Now, as a reminder, tomorrow or at the end of the second sprint is also for those of you who have signed up under an OBL, the objective-based loan, or however your financial commitment to Bull Tech looks like. So like your deadline for withdrawing is essentially the end of this week if you do not wish to continue on. I encourage you to continue on. I've seen a lot of success from many Bloom Tech learners, and you've got a lot of exciting material coming on for you down the road intellectually. But of course, if you have any questions or if you have any concerns about your standing, note that I'm more than happy to chat with you, send me a message, or we can meet one-on-one for this. Additionally, you want to remember that this is the second sprint challenge where you need to get that specific 100% on the sprint challenge and 80% or more on the sprint assessment multiple choice questions. I think we had some concerns over like the answers not being like the answers you got wrong in the sprint assessment, the first sprint challenge. I think I've adjusted that for sprint 2, but if you have any concerns or any issues come up, please make sure to send me a message and let me know. Any questions before we dive right in?
Just to clarify on the stuff, it's the first attempt though on those are due on a
first
time?
attempt. That's correct. You need to make a first attempt, but if you don't finish, like
right,
if you just honestly, this is not me recommending that you do this because it actually really I do have a few learners who submit a 0% sprint challenge and then they don't work on it until the last week. I don't recommend that because usually those are the learners who are like, I'm so behind on everything. I'm like, yeah, you are. So,
but that day would be on Thursday though, or that would be Friday?
No, that would be the Wednesday. So the last day where you can turn in your sprint challenge and sprint assessments.
No, the first attempt.
Oh, the first attempt. No, the first attempt is due Friday. So
Friday. Okay, cool. I just wanted to nail that down. Cool. Thank you.
Yeah. So it opens up Thursday, tomorrow night, and then you have till Friday end of day to have made a submission. Yeah, good clarification. Okay. Let's dive right in. Now, before we dive into our statistics notebook, don't worry if you don't have this, I'm not going to add too much of this. I just want to make sure that we are clear on a few of the symbols or the signs of what we're going to be seeing as part of our equation today. There are two very specific equations that we're going to be working with. One is the equation for conditional probability, which is closely lined up with the equation for Bayes' theorem. Curious thing about Bayes' theorem, which I'll go into in just a moment, is that as any component of an equation, you might end up using that equation in different contexts. And as a matter of fact, the equation itself has changed since the inception of since the first iteration or the first inception of this equation. You can see slight adjustments. We're going to be working, and your assignment's going to be focusing mostly on the simple version of the Bayes equation. But note that that is very much aligned with the equation for conditional probability. Now, in order to understand what the parts of that equation look like, we need to understand what these two symbols mean. Let's say we have two sets of values. We can expect both sets of values to be identified as A, the even numbers between 1 and 10, in other words, 2, 4, 6, 8, and 10, including 10 in this scenario. And then our prime numbers is our set values for B, 2, 3, 5, 7. But the intersection, or this value, really refers to the symbol for all the values that are shared between two sets of values. So if you look at your Venn diagram, very much like we used to work with our merges and our joins, you can expect to see that your intersection can be identified by all of the values that are shared between both sets of numbers. Alternatively, in this case, the union, as it's mathematically recognized, again, this is not the same term for union as we would use when doing a concatenation or a merging. We are not stacking a data set on top of the other. The union in this case, with this symbol, kind of really very much shaped like a union, is referring to the set of elements in A or B. So essentially, you can expect all of your values to be included. So in this case, in our example, that means that a union of A and B will actually be all your sets of numbers from both sets. 7, 8, and 10. Right, that part's pretty straightforward. But then what would your set look like for a set of values between A, or the intersection of values between A and a B? I'll answer for us, it's 2. So in this case, 2, because the 2 is the only number that appears in both sets of numbers. So this is how it's referred to mathematically from a component of two different series of lists. In the terms of conditional probability, what we are using is including these types of features from our data frames and including both sets of features as one particular object. And we'll see an example of this in just a moment. Now, the other type of symbol that you can expect to see, or that we are going to be working towards, is this P round value X, which simply refers to the probability of X, or if X is an event or a specific numerical value, or if it's an event to which you can quantify, which is what we're going to be doing a lot of today, you can expect to see your symbol delineated as the probability of X. The other component that you can expect to see is the probability of X given B. And note that we use the pipe symbol here in reference to that term of probability of X given B. And what this refers to is a little bit different from the probability of two separate independent events occurring together. What this refers to is the probability of an event occurring given that another event has already occurred. Note that slight differentiation between the two symbols or the two concepts. One is, what is the probability that both of these things happen? But the probability of X given B refers to what is the probability of something happen given that this other thing has already happened or has already occurred. This fits into the general principle of the equation the equation that we're going to be looking at, because we'll be measuring using the law of conditional probability different events occurring given that other events have occurred already. So with that, let's go back to our notebook for today. Let me get rid of my Venn diagram here for a sec. Any questions so far? Great. So here's what exactly we're going to be talking, or what we've been talking about. Up until this point, we've been running a series of hypothesis tests using a degree of set or consistent enough distributions. So up until now, we've been working with our normal distributions. We've been using all of the theories that are applied to our normal distributions. And we've been using different statistical tests in order to come up with conclusions based on where those conclusions fall as part of the normal distribution. This is a concept where the results can be expected to be replicated over and over again. As any scientific method would tell you, a scientific theory or a scientific conclusion can only really be accepted if we can see those models, or we can see a specific result being repeated and repeatable over and over again. Frequentist statistics, or the components or the type of statistics that we've been working on over the last 2 days, is essentially banking along this idea, where if you run a specific test or a specific distribution over and over again, you can expect your results to fall within one portion of the distribution, in this case, our two-tailed distribution. If your values fall within those small probability sections, you can accept a alternative hypothesis by rejecting your null hypothesis. So, as part of a philosophical approach, if we can frequently see the results from our exercises, we can come up consistently with a conclusion. Bayesian statistics takes that approach and sort of reverses it, in the sense that whereas frequentism uses our knowledge of our sample and a population, we take our data and draw our conclusions. A Bayesian approach looks at a specific conclusion and potentially tries to reiterate or reconsider the data that you're working with. We'll talk a little bit more about that in just a moment. But first and foremost, let's address why we would actually work with a different type of statistical philosophy, or what we're going to be doing today. So Bayes' theorem is built into a number of the machine learning processes that you'll be learning about down the road. So if you're interested in any type of categorical or neural network type model, a lot of what happens with a neural network, actually, let me go ahead and just do a quick drawing of this, is that you start off with a certain set of values, or you start off with a certain set of data sets. You submit those values into separate sets of nodes. Those nodes will eventually process or make a series of adjustments to your data set. And based off of what that formula, or what formula you apply to those individual nodes, you can expect your results to change. And as those results change, you can submit your modules to a different set of nodes or modules. So essentially, what you're doing is you're taking a specific data set, putting it through whatever model or whatever type of neural network model you're trying to process. You put that data through a series of changes. Within that very model, the network, the data set itself and the conclusions change. And based off of those changes and those results, you're essentially running those models through a separate test. Now, it's obviously a little bit more complex. The neural network itself is looking at a series of different planes and a multi-dimensional set of array calculations. But when you're looking at your final conclusions or your final calculations, the reason you get the conclusions from that neural network is the series of changes that the model has essentially gone through. And this is all based on a series of Bayesian philosophy, where you can reject the idea of just having a specific conclusion, but you're adjusting your conclusion based on the lessons you've learned from a prior model. this is very much some fun Unit 4 material that you'll have a chance to work on very really 3 months down the road. So before we get to that, let's actually understand what's happening with Bayes to begin with. Give me 5 seconds here. Okay. Just making sure I've got my notes together. All right. So let's start off by actually looking at the law of conditional probability. This is a very specific rule for those of you who've had some time, like who've taken any college statistics or even high school or some level of high school statistics, you can expect to see this. But it's a fairly straightforward formula where the probability of two events is going to be equal to the probability of an event occurring along with the other event. So both events need to have occurred, and you can quantify the probability of that event occurring and dividing that by the probability of the second event occurring. This is returned as a value for the probability of A given B. So essentially it's if A and B have occurred divided by the probability of B, you can essentially interpret this same event of both of an event having occurred given that second event occurring. So if we were to take a look at the example of our Titanic data set, we can interpret using some of the functions we've actually learned from yesterday. So if we have two separate events on the Titanic, we have the probability of A being the event of surviving the sinking of the Titanic, and B, the probability of being a male passenger on the Titanic. We can essentially assign those values to different to these different components by starting off the probability of A given B is the probability of surviving the Titanic given that your passenger was male. The probability of A and B being the probability of surviving and being male. And finally, probability B is the probability of being male on the Titanic. So if we have those three components, we've actually got enough to start calculating what the what that probability is going to look like. So we can actually build in this equation. We could essentially do it by hand. We will do some of that in a certain extent, but let's first actually use the pandas crosstab method to see these probabilities in actions. Let me make sure I've run this data set. So I'm going to use the pandas crosstab method. And I'm going to call for my index values the probability of the passengers' genders and for whether they survived or not. Let's take a look at this. Let's take a look at our margins first. We've got our total values. So from this crosstab, we can actually take a little bit of information from the Titanic breakdown, based on the law of the law of probability, out of 887 passengers, 573 of those passengers were male. That part's fairly straightforward. But if we wanted to calculate all of these quantities, we can actually show how the probability of A given B is going to be equal to the probability of A and B divided by the probability of B. So let's start by looking at those values and assigning them one thing at a time. So the probability of B, pretty straightforward, is 573 divided by 887. And we should return a potential value, 0.64. Easy so far. Let me make a quick note. This is one of those circumstances at the stage we're at where you can actually start calling your objects by indexing the values. So if you've got your Titanic cross, to refer to my crosstab object, I can then take my crosstab object. I'm actually going to need to see where they're located. and call on those objects by indexing. And there's a bunch of ways you can index for those values. I personally like to use the loc function because it helps me identify where a value is located. So if I want my 573, I can call my male index values along all values. If you run this, you'll see this returns the number 573 because that's the value I've called. Of course, I'm dividing by 887, so it's simply calling the values for Titanic cross, loc those values, I'm calling all and all. And the reason I like this method rather than just writing out the numbers, which is okay, is that if the numbers change in my data set and if for whatever reason I end up using a different data set, or if like I end up changing my how the order of male and female is appearing on the row number, this method male.loc male all essentially calls the index values that I'm looking for. So it's just a little bit safer to call the values in the event that these numbers may potentially change. So let me set up a code thread for this first bit. And this will get us started. Any questions so far as to what we're doing at this point? We're really just assigning a value to the probability of B. Let's actually get a little bit trickier here.
That's what I was saying. We're just getting to it, right? Because we did this yesterday, essentially.
Yep.
Cool.
So yeah. You're going to see a lot of yesterday in today's first part of the course, the second part, or the first part of the notebook, and the first part of your assignment. The second part of your assignment ends up being a little bit more of a logic game, which is kind of fun. So we'll talk a little bit more about that in just a minute.
On that note, just because you said logic games, a lot of this does remind me of the actual math behind like the law of magic, like logic games, and those were a lot of fun. I really enjoyed those. So
give me a thumbs up just so that I don't give myself away and I don't bore you to death. What's the name of it? I forgot the name of it. I'm blanking out on the name of it. The door game. The Monty Hall problem. Give me a thumbs up if you're familiar with it. No one? Oh, you're gonna hate me. Oh, the end of this notebook, I'm just not gonna be anyone's friend at the end of this logic, at the end of this game. All right. Oh, I'm so excited. Let me make sure we've got the attendance code because this just got fun. Where is my attendance code for today? Where's my attendance code? Nope. Where's my notepad? There it is. Day 6. We're at day 7. And our attendance code today is 4362. Make sure to share that with you. 4362. 4362 is your attendance code for today. All right, let's move forward. So now it's the probability of A and B. So this is our value for the probability of both events occurring. That's this top part of our equation. So probability of A and B, or probability of A intersection B, however you prefer to refer to it. This is the case where we have both passengers who were male on the Titanic and who survived. So it's both elements needing to have been met. Now note, we actually have that value already assigned. It's 109. Those are the number of male passengers who survived the Titanic after the fact, but note we're looking for the probability. So it's actually 109 divided by our total value. So I'm just going to use my loc method to call those objects. So I'm locating the values based off of the male passengers who survived. Let me just make sure this runs on its own. There's 109. And then, of course, we're dividing by the total values of all passengers on the Titanic. So in this case, we have 12%. So if you were male and you survive the Titanic, you are 12% of the population of all the passengers who were on the Titanic within this data set. So let's finally note one more component. No, we actually have all we need, really. So with that said, we've got our probabilities. I already forgot what I'm supposed to be printing. Probability of P and B, and the probability of A and B. Okay, so the probability of being male on the Titanic is 0.60. Let's round it up to 65%. And the probability of surviving and being male on the Titanic is 0.12. So in this case, if we were to follow up and create our equation for probability of A given B, that equation would look like, and note with markdown, you can use dot fraction and these curly brackets to essentially account for those values, is the fraction of probability of 0.12 divided by 0.65. Now, you can actually account for that as our probability of A given B will be equal to the probability of A and B divided by the probability of B. So a lot of different, there's a lot of the letter P in there. But when you run that equation, you're seeing that you've got a probability of the probability of A and B is going to be 0.19%. So that is the first part of the conditional probability equation. Now, if we wanted to check to see if this matches with our ability to actually gather the conditional probability, we can actually use the crosstabs, built-in methods to determine those values. So this is how the equation works on its own, but PD crosstab will actually do the hard work for us. So if I take the same crosstab value that I included up here, and look at the normalized values, we can actually measure these values along the index. I've got an error. It's crosstab, and the error tells me it is unexpected F. That generally means I am missing a parentheses. And we are now missing columns. Typos, all about. There we go. So there's our 0.190227 delivered in one quick normalized value, because all this is essentially doing is the conditional probability of these values. So if we wanted to alternatively turn this around on it, so we have the A being the surviving and the A, essentially if we wanted to kind of flip the script on this, so rather than looking at whether a passenger survived, given that, so if we wanted to determine whether a passenger survived, whether a passenger was male, given that they survived, we can expect that to be 19%. But if we inverted the value, this is a quick note that shows why the given is so important. If you were to flip this around, so instead of having your values on the survived, you've essentially turned this around, you'll notice that your probability changes. So in this case, the probability of being male, given that they survived. So after the fact, it's who were the survivors of the Titanic? What was the probability that they were male? You actually return those values as 31% or 32% to round up. Note, there's like a very subtle consideration here because it's just the order of events or how an event gets calculated. In this case, we're just looking at the survivors and determining how many of those passengers were male within those survivors. So however you want to talk about it, this is what conditional probability essentially addresses. Given that this event has already occurred, what's the probability of that event? What's the probability of this other independent event occurring? And this is probably the moment to ask any questions so far. Oh, I lost someone. Okay, so why does this matter? Or why is this important to consider? Welcome back. Give you a second for the audio. All right. So why is this important? Because the thing about Bayes' theorem is that, interestingly enough, although statistics is one of those philosophies and one of those mathematics that has been in place for thousands of years, yeah, this is just something we've been doing since the beginning of like common applied mathematics. The Bayes theorem has only actually been put into practice in, I think, as an active approach. It's as an active approach. It's only really been used for the last 100 or so years, because the computations in order to iterate through so many different mathematical components wasn't really available until the rise of the computer, of modern, or like some type of modern computation. So it's been kind of talked about and considered, but it's never actually been put into practice in any applied method until the last 100 years. But when it was first developed, it was delivered by this English minister who we're not really sure we know a lot about. We don't really even have a painting. There's one painting that's been misattributed to him, but the theory that gives this minister his name was part of a essay that was written back in the 1700s. So the idea is he wrote this essay, and to be fair, he wasn't that really impressed with his essay. It wasn't really published until after his death. It was brought to the Royal Society in 1763 by a friend named Richard Price, who eventually ends up being a famous statistician of his own volition. So it essentially concerned how we formulated probabilistic events about the world when we encounter new data. So the person who delivered the thesis behind this theorem was Richard Price. And if we kind of consider how this story is told, it's essentially, think about the first person to come out of the first person. Let's picture the story of the first person coming out of a cave, or a person who's been living in a cave forever comes out into the world for the first time. They see the sunrise. That sun rises and then falls down. This is a really big deal. It was like, wow, that's really impressive. But then it happens again the next day. Oh my gosh, this big burning thing in the sky came out again. Okay, it happened again that second time. Then it happens a third time. And after the fourth or fifth time, you're just kind of like, okay, that burning thing of fire in the sky is apparently just doing this over and over again. But it's that process between that first time you see the sunrise, the second and the third. It is essentially going from a freak occurrence, or like this miracle occurrence, into something where you're like, this is seeming to be a very consistent aspect to the world. And so with every rising day, you can begin to say, well, I can expect the sun to rise tomorrow because it's been doing this consistently for as long I've been outside of this cave. But here's the thing: there's a good reason to believe that you can expect the sun will rise, but let's be honest, you can't really be 100% certain about it. Could be that we're living in a computer simulation, and one day the computer simulation, the Matrix, decides, it was like, you don't get a sun today, ha ha ha. And that the probability of this is probably very unlikely because that's never happened before, but we can never be 100% certain. And so the argument is that the world is intrinsically probabilistic and uncertain. This is still part of a component of how you think of the world. Bayes was indeed a believer in divine perfection. He was an English minister, so he was very much a big part of the philosophy of the world. This happens during the Enlightenment, and a lot of what people were trying to do during the Enlightenment was trying to find proof for or against the existence of God. And Bayes was essentially one of those individuals. We were like, I want some scientific proof of the existence of their Christian God. Now, Bayes was also a fan of Sir Isaac Newton. So both of those things were essentially like things that you had to kind of work with each other in order to find the scientific response to like the existence of God. So the idea was, if we can take a specific approach, can't you use certain components about everyday existence to determine whether God exists or not? So the idea falls, just trying to make sure that I speak this a little bit more clearly. If we have a certain event occurring, or if we have a certain amount of data from an event, can we predict the probability of an event occurring given a specific cause? Can we predict the probability of A given B, given that there are humans on Earth, given that we can interpret that there is both good in the world and bad in the world? How can we use this cause to determine the event of the existence of God? So this philosophy is, this is kind of where the philosophical component comes into place. So from a history perspective, this is how the philosophy starts. Can you use the data we do have to look at a prior event having occurred? So they essentially used the law of conditional probability to start building out this equation. The problem was that, for one, Bayes was Presbyterian, so there was a certain amount of lack of acceptance within the churches they were working with. So there was a lot of kind of back and forth on this. And this continued to be part of a little bit of a controversial equation, because if you take your law of conditional probability, if you take this rule and you essentially start to convert the rule into a new equation. So if the probability of A and B is equal to the probability of B and A, both things are the same. We can also, through essentially changing the approximation of by changing the location of these specific values from the probability of A and B, we can change this value to being the probability of B and A, which would also be the same as the probability of B given A times the probability of A. So when you substitute this into your original formula, you will get the probability of A given B will be equal to the probability of B given A times the probability of A divided by the probability of B. So you create two separate events and add the probability of B given A, or the certain event or the certain conclusion of the event. And with this conclusion, you can essentially approach the reverse conclusion of those values. Let's take it down from mysticism and religion, and let's lower the stakes a little bit. Let's talk about cookies for a second. These are the ones you can eat. But let's suppose we have two bowls of cookies. You have one bowl that contains 30 vanilla cookies and 10 chocolate cookies. So 40 cookies in one bowl, and then 40 cookies in a second bowl where the values are equally split. So say you reach into the bowl and randomly, and without looking which bowl you've reached into, you've picked that cookie. The cookie is a vanilla cookie, and you're trying to determine, well, what is the probability that this cookie came from the first bowl? So this is what this is what we're referring to when we're looking at conditional probability. The Bayes rule essentially means that because you have a result, you can actually come up with a conclusion about the cause, or about where that cookie came from. So if the probability of B is for the event that the cookie came from bowl one, and B is for the vanilla cookie, you can essentially look at the equation, and we're just converting our values to the probability of the cookie coming from bowl 1, given that it's a vanilla cookie, it's going to be equal to the probability of a vanilla cookie, given that it came from bowl 1, to the probability of that the bowl came from, that you essentially took it from bowl 1, over the probability of this being a vanilla cookie against the total values. So let's assign each one of our values first. And let me just, I thought I had this as a specific data frame, but okay, I guess we'll type this out, unfortunately. Let me just make sure. Okay. All right, so let's just go ahead and fill in the blanks. Slows this down a little bit, but all right. So the probability that we chose bowl 1, unconditional by the cookie we got. So we essentially chose a bowl at random. The bowl is essentially one side or the other. So that probability is 50%. You either reached into one bowl or the other. A quick thing to note, and this is going to consider how you think about your assignment today. What happens if there was just one bowl? If it's just one bowl? What's the probability you would assign if instead of 2 bowls, you've only got 1? 1, yeah, it's 100%. That definitely came from bowl, the only bowl you have. So keep that in mind when you're thinking about like your assignment later today, because it's kind of some things to consider there. So if your probability that your vanilla cookie came from bowl 1, you can assume that your probability was from either bowl is 50%. So let's say that the probability then that you got a vanilla cookie from bowl 1. In bowl 1, there are 30 vanilla cookies out of 40. So the probability of getting a vanilla cookie from bowl 1 is actually 75%, or 3 out of 4. Finally, the probability of vanilla cookie means what is the probability that you got a vanilla cookie from either bowl. So you just take both bowls, throw them together. Now you have 80 cookies in total. Because there are a total of 50 vanilla cookies, you would say that the probability of your vanilla cookie coming from, or your vanilla cookie coming as a total value is 5 out of 8, or 5/8. So this means that the full equation would look something like this. So once you put it all together, you end up having an equation that looks at the vanilla cookies, or the probability of your, once you essentially put all of these values together, half times 3/4 divided by 5/8, you get 3/5, or 60%, is the probability that this came from bowl 1, given that it is a vanilla cookie. What then ends up being the situation if the probability of, like, if 3/5 is the probability that this came from bowl 1, what is the probability that it came from bowl 2?
Two-fifths.
2/5, that's
Or-
right. Yeah. So you can essentially determine from those statements that there's a greater probability that your cookie came from bowl 1. That's 60% as opposed to 40%. And this is in the simplest term, this is what the Bayes theorem is essentially putting together for you. So the question I often get at times with this example is that, okay, but what happens if one of the bowls happens to be bigger? What if there's an unbalanced bowl? Well, you can essentially take that same principle, and the only value you need to change, say, for example, you have a bowl that's a little bit closer to you, so you can measure the likelihood of that bowl being closer to you. You could, let's say you can measure it that there's a greater probability it came from that bowl simply because it's closer to you. Well, that same equation would look like, so if you've got an unbalanced bowl, let's say that it ends up being 25% more likely that it came from bowl 1. The difference is that instead of 0.75, the probability of your bowl, coming in from one of the closer bowls is increased by 0.25. Your 3/4 stays the same. So these values stay exactly the same. and your 0.60, this is 0.625, will have adjusted. In other words, because that first bowl is now a little bit closer, you've now got an unbalanced probability of a bowl being closer to you. So now the probability that this came from an unbalanced bowl 1 has improved with, of course, the opposite of this value, bowl 1 prob. The probability of your value coming from bowl 2 is simply 1 minus bowl 1 prob. So note, the probability of the other bowl is pretty straightforward, 0.10%. And this is important to note because the way you assign which value is more likely, you end up working based on which value has the highest probability for a value to occur. So cool, that's how conditional probability works. But how does that really apply to the philosophy we've been talking about? How does that apply to everything we've been working with? Because Bayes' probability doesn't just limit itself to one calculation of a conditional probability. It takes into account the sun rising every day. It takes into account that, hey, if we are continuously seeing a different result, or if we're continuing to see a result, how well does our, how much does our philosophy change? Well, the idea that comes out of this framework is the idea that your initial belief, given new data, will adjust that improved belief theoretically. If you're seeing that in this scenario, you're still going at these bowls, and you know there are different numbers of cookies, but you still are getting vanilla cookies. At some point, you have to suspect that the breakdown of vanilla to chocolate cookies might not be exactly what you think it is. And the way this was essentially put into practice, and the reason it wasn't very actively used until the beginning of the 20th century, has to do with the fact that we didn't have the computing power to begin to continuously iterate some parts of these equations. So the Bayes theorem was essentially a big part of how Alan Turing used his the German Enigma machine. This is a machine that was used to crack the communications occurring between different submarines or German submarines. So the idea was, rather than trying out random codes, Alan Turing would kind of determine what the probability was that the code would use certain keys more frequently than others, and essentially shrink the probability of those values being used. This was also a big component in the development of Claude Shannon's, or how Claude Shannon essentially took part in building the computer byte. The computer byte essentially allows you to apply certain information to that specific byte. And with that computer byte, as it iterates through different values over and over again, as you combine two or three different bytes together, you start getting additional or new information. So why does this end up being controversial as a concept? Because you're not working off of a specific or a set data or a set of data that you can conclude. The idea between a Bayesian versus a frequentist inference is that there are specific components that need to be met in the frequency of a value occurring to be part of an expected population distribution. So in your notebook, you can actually look over the XKCD comment, where the idea is that frequentists tend to kind of devote so much time to their p-value. And because your p-value is less than 0.05, you can make certain conclusions about the data frame. Whereas a Bayesian interpretation could essentially be like, betcha 50 it has it. But the general concepts behind the philosophy of Bayesian inference is that with a frequentist approach, you're talking about being able to run an experiment multiple times. Whereas the priority given to a Bayesian approach is to not just the long run frequency of those experiments or the probability or the p-value of that specific experiment, you essentially put a much larger emphasis on the degree of belief of a specific event occurring. Now, the approach when we talk about what values are fixed versus what values are not fixed can be sort of defined by an example using emperor penguins, where here's the thing, a frequentist approach will say, at this moment, at this point, there's a set number of penguins' height. So every penguin is going to be a specific height, and we can expect that there's some alien or some god that knows the exact true mean of all of the penguin population. You know, when we work with our samples, we take our samples and then we determine what the confidence interval might be for us for a specific sample. But the Bayesian approach is, well, except for the fact that penguins are dying and being born every moment of every day. So there's constant change happening to any given data. So there really can't be a single answer to the true population mean. So there's a certain amount of uncertainty that we need to be comfortable working with. The basis behind the types of equations that we're working with, up until now, we've been focusing at the sampling distribution, normal distribution, the t-tests for our different experiments. Bayes' theorem is essentially just a simple equation that returns a conclusion for you. In a lot of senses, the way you draw these conclusions are based on the order of which, what is the probability that you're seeing this data within a frequency of values? Whereas a Bayesian approach tends to look at the probability of having this conclusion given the data that you're seeing. And the biggest component is that although you're both working off of any given data, you're actually putting a certain amount of emphasis in your prior belief from your data set. This is where things get controversial, because the degree of belief can be a very subjective concept, because what I believe might be very different from what you believe, or the probability of something happening may be slightly different from what you believe as well. In a lot of ways, the reason this didn't really gain ground until we could actually use computers to do the work for us is because when you didn't really have a prior belief about a specific probability, you just assigned it to be 50%. You either had or did not have it, which essentially brings you back to square one, and means you're essentially calculating on a frequentist value anyway. So Laplace, the same person who came up with the central limit theorem, essentially ends up working with the Bayesian formula for a long time before eventually coming back to frequentist statistics. But this is a person who actually worked really well at kind of navigating both types of philosophical approaches. Okay, I've been talking quite a bit, but most of it is just kind of philosophical mumbo jumbo. But any questions so far? Mumbo jumbo, wrong word for statistics.
It just seems that the Bayesian and then the frequentist are just like two different people completely, right? Where they go through how they want to do something in totally two different ways. One wants to do a lot of work, and the other one's like, I would rather just make it easy.
All right, no, okay. How many of you are familiar with Nate Silver?
No.
I know. Okay, so I know. So here's the thing. Nate Silver, probably not a very popular person right now. I actually use one of his examples in just a moment, so my apologies in advance. He was, I mean, so for those of you who don't know him, he was, he's got the website 538, which for a while was really good at, essentially became known as the place where you would go get your election, the probability of a specific candidate winning any given election. He became very famous because he was really good at making baseball predictions. Justin, you're about to say something.
That's where I heard him making predictions in baseball and basketball. That makes sense. He
became very good at making baseball and basketball predictions. Eventually, he tried using the same statistical function, which like uses a little bit of the Bayes formula to apply it to congressional elections. And he actually, this was back in 2004 and 2008, started doing really well. In 2008, he put that same formula to the Obama and McCain election. I am aging, I'm showing my age. to the Obama-McCain election and actually did really well, almost predicted every single electoral college vote in where it was going to go. Became really famous, and eventually it became someone that you could rely on their maps for elections. Even at that time, he was fairly unpopular in statistical circles because of his deep emphasis on Bayesian statistics, which essentially formulates, look, I can only tell you that there's a probability that one thing is going to happen versus another thing that's going to happen. In 2016, he became, a lot more people became very angry because his 538 election had Hillary Clinton winning by in 70% of the models that were run. But Donald Trump essentially won with, I think at that point it was like 28% of the, there was the probability that Hillary Clinton won 70% of the times that he ran these models. However, within that same model, 28% of the times that you ran these models, you had Donald Trump winning. Donald Trump, of course, wins the election. And because of the expectation of but 70-30, those odds, how could you, it essentially ends up making him not very popular. Because of a general understanding of how the specific model works, which is not saying that there's a 70% chance that you'll win. It's like in 70% of the times that we ran this model, Hillary Clinton won. However, there are a bunch of other factors to consider that may not be fit into this particular model. And it just so happened, yeah.
That's where then that difference between Bayesian and frequentists would come in, where they're like, well, you missed all this stuff. You should be putting that into your equation.
Correct. Exactly. And this was a big, big component. One of the biggest complaints was that how many unknown variables election statisticians were working with. That is one of those, 2016 was one of those famous elections where when you polled people due to for a multitude of reasons, you had a much larger number of voters who either hadn't made up their mind until close to election day versus people who just didn't wish to answer. So there was a lot of missing data included in this series of in these different sets of models. So he's a modern Bayesian, and he is still very insistent upon how well his models work. Because if you think about it from a perspective, yeah, the world we live in is a world where the 30% of the models where the model that occurred 30% of the time actually occurred. So with that said, where am I going with this? Right. Let's go back to the equation itself. Because we can actually look at the different components of this value. And yeah, you're absolutely right. Very different people, very different ways to approach a specific problem. However, there's very much good use case scenarios for either one of these philosophies. It's just very much a matter of how much value do you want to assign when you don't know when you can only assign what is the probability of something happening, or when you don't have necessarily the data you might want or the prior information you might want. So because you can essentially reconstruct your conditional probability into a different equation, that means that each one of these parts of the equation essentially serves as a proxy for a specific event occurring. And this is where the equation can get measured out, and where your prior belief or whatever prior information can be assigned a specific value. Because as long as you have 3 individual parts, you can come up with a conclusion for a specific event occurring, because that's essentially how conditional probability works. So in this case, it's important to note, let's define what these parts are. The posterior probability, or this value above, is the probability of what we're trying to find out. That's what we're trying to calculate. The likelihood is what we would generally consider normal hypothesis testing if we were frequentist. In other words, this is what is the likelihood of a specific event occurring. And the likelihood of a specific event occurring is that if we were to see a specific event and it occurs over and over again, what do we expect? How frequently do we expect that event to actually occur? The prior is essentially our prior knowledge or our subjective, to some extent, belief about a specific incident, about a previously occurring outcome. And finally, the evidence is like the data. Let me go ahead and recorrect this. So the evidence is data. So the evidence would be the data that we have from that event or an experiment. So as long as you have those three components, and as long as you're able to define those three components, you can actually come up with a specific equation that measures a posterior probability. Now, it's not just about a conditional probability, because the way this works is that we can take the information and our conclusions, and we can reiterate that, or we can reiterate through that, that conclusion. In other words, we can make a posterior value a prior part of our equation. So we'll talk about this with a couple of examples in just a moment. This is a good time for a break. Let's come back at 14 after the hour because I need a glass of water.